Today we're going to talk about curved mirrors, which are mirrors that show up in rear view mirrors and are used in things like telescopes, and they behave differently than flat mirrors do. You can think about the curved mirrors we're going to talk about as being part of a sphere. And so here's a sphere of radius r. So suppose you sort of cut off part of that sphere, and that's how you can picture this concave mirror. Now when we deal with these mirrors, we're going to find what's called the principal axis, which is just a line going straight through the center of the mirror. And we define this C. This C is the center of curvature, which is just literally the point where the center of the sphere that this mirror used to be a part of. And so the concave mirror will work like this. A light ray coming in that's parallel to the principal axis will be reflected inward like this. And if you look here, what this is so even though this is a spherical mirror, you can sort of take this little part that it reflects on, and you can sort of say that that instant where, or that sort of little point where it reflects acts like a flat mirror. And so if you look here, the theta of incidence equals the theta of reflection, just like with a flat mirror. Okay, it's just that with the concave mirror, the sort of angle of each of these little tiny pieces is going to be different. Now the other side would be a convex mirror. So really the only difference here is just the part that you put the reflective surface on. So with the concave, the reflective surface is over here. With the convex, the reflective surface is over here. And so it's basically taking this and turning it around. And if we do this, the light ray will bounce this way here. And again, this is the sort of same idea. If you were to look at this one little spot here, this sort of behaves like a little tiny flat mirror, and the angle of incidence will again be equal to the angle of reflection. So again, the rules for a flat mirror are working here, just a slightly more complicated situation. And just the definition, C is how we define the center of curvature, which again is just the center of this sphere over here. Now let's look at a concave mirror a little bit more closely. And so we see that these rays that come in parallel to the principal axis, okay, and again each one is bouncing off its little piece there. All right, what happens is these are going to be focused at this point we call the focus. So rays parallel to the principal axis all pass through the focus F. And the distance F from the center of the mirror is called the focal length. And so here's how we would define this here. It's called F, and it works out to be half the radius of this circle that spherical mirror is made up of. Okay, so the focal length will be R divided by 2. For a convex mirror, there'll be a lot of similarities, but here, instead of focusing the light, it sort of makes the light more diffuse. And so it bounces the light off, and so instead of bringing the light beams together, it makes the light rays kind of go off. But now if you take these light rays and backtrack them, okay, what happens is it looks like they're leaving from a point which is that same focus. All right, and so there's some relationships here, obviously. And so rays parallel to the principal axis appear to originate from the focus F, and the same sort of idea. This focus is still half the center of curvature distance, and we're going to see though that we define this to be negative. So with the focal length, if it's in front of the mirror, we define it as being positive. If it's behind the mirror, we define it as being negative. So let's look at some real quick questions here. So what kind of spherical mirror, concave or convex, can we use to start a fire? All right, so it would a concave mirror. So that again focuses the light rays in front of it at the focus, and if you put something like here in this picture, there's a match there at the focus that can light up and start a fire. How far from the paper to be ignited should the mirror be held? Well, obviously I just said that. It should be at the focal length. Now, with our mirrors, we're going to be interested, like we were with flat mirrors, in where our image is. And we're going to learn two different ways to do this. One is to actually draw light rays that give us kind of a more physical intuition of what's happening. And another way, we'll use a nice equation, which can obviously do it usually much faster. And so for the light rays, so here's our eye, and we're assuming that this arrow here labeled O is our object. And so here we have a concave mirror, and the way that it works is there's 3 special rays that if you draw, they will come together at the point of where your image is. And so here's the 3 rays. So the first one is parallel to the principal axis, and if that happens, it should reflect through the focal point. Okay, so and what we're doing is we're sort of shooting our light rays through the tip of our arrow. And what should happen is where these light rays meet, or appear to meet, will be where the image is. Our next ray is through the focal point, and if that happens, it'll reflect parallel to the principal axis. And so this ray comes through the focal point, so it has to come in at an angle because it's going through the tip of the arrow and then the focal point. And if it does that, because of the way this mirror works, it'll shoot off parallel to the principal axis. So it's in a sense just the opposite of the last one we drew. And then the last one is through the center. So a light ray that goes through the center of curvature will bounce straight back by definition. And so here we draw it through the tip of the arrow, through the center of curvature, and it bounces straight back. And these three rays, you can see, meet over here. And so if my eyeball is over here, all right, these rays will come to my eyeball in theory, and then I will see the image as being where these light rays emanate from. And so that's the point right there, my image. And so if we look at this image, there's things that we're going to talk about to describe the image. And so the first thing is this image is real. The light rays actually cross there. We talked about this briefly last time. The image is inverted. The arrow points in the opposite direction. And it's diminished, meaning it's smaller than the object. And then just so you know, any other ray from the object tip which hits the mirror will reflect through the image tip. So here's just some random ray. We don't really know how that one works, but we know that it has to bounce through there. And so once we have that point, we know every other ray should point through there as well. Now, we're going to look at ways to calculate some of these things we're talking about. And one thing that we're very interested in is sort of the magnification of our image in our object. And so here we can draw a ray going through the tip. And this is the real simple ray. It goes right to the center of the mirror. And so this is going to be the angle of incidence and the angle of reflection. That should be equal. And we can make little triangles there. Now we're going to define distance DO is to be the distance to the object, and distance DI to be the distance to the image. And then distance HO to be the height of the object, and distance HI to be the height of the image. Now these are similar triangles, so what we can do, like I said, this is the angle of incidence and angle of reflection, is we can set up tangent theta equals HO over DO, and that should equal negative HI over DI. Of course, that negative is because here this HI is in the negative direction here, so you have to account for that. And we define the magnification to be HI over HO. So the magnification is the ratio of the height of the image to the height of the object. And so we can find that one of two ways here. If we happen to know those heights, we can do it that way. But an alternate way, again, sort of solving from this tangent theta, is that it's the negative DI over DO. And the way this works is M will be positive if the image is upright. It'll be negative if it's inverted. So some of those pieces of information that we got from drawing that picture we can get from this equation. All right, so let's pause and ask ourselves some questions dealing with this new concept. So here we have a mirror creates an image of the 4-inch arrow shown with a magnification of -2. What is the size of the image? So think about this. All right, and so hopefully you got 8 inches. If we just take that equation, our definition of magnification, it gives us the size, and so we can solve h of the image equals m times ho. And so the object is 4 inches, so 2 times 4 negative gets us 8 inches. Technically it's -8 inches, but we're just asking for the size of it. And so what direction will the image arrow point? Well, that's where the negative sign comes in. So the image height is -8, and so that tells us that the image is inverted. And so since our arrow here is pointing down, our image would be pointing up. So that sign tells us it's inverted from the object direction. Now, like we mentioned, there's an equation to solve this. And here's the equation. It looks kind of like our equation for capacitors in series or resistors in parallel. And so it's this equation like this here, and it just depends on some of the things that we've been talking about. So the way this usually works is it's nice to draw the rays and see how this kind of works physically, but this is how you want to do it if you're doing calculations. And so the F is the focal length. Again, that's positive if it's in front, negative if behind, so positive concave, negative convex. D0 is the distance the object is from the mirror, and our same sort of definition works. It's a positive if the distance is in front of the mirror and negative if behind. We'll sort of show you how this works. in different kinds of cases. And then where the image comes up will be di, the distance the image is from the mirror. And again, that's positive if in front, negative if behind. And so you got to be real careful with your signs. And so here's a problem. This is sort of the same thing we've been working on. Let's say an arrow is placed 6 centimeters in front of a concave mirror with focal length of 2 centimeters. Determine the image location. And so we get that the arrow, which again we're sort of using the same picture, so that's 6 centimeters. It's in front of the mirror, so that's a positive 6 over here. This is the focal length is 2 centimeters in front of the mirror, positive 2, and we take this equation and solve for di. And so we get 3 centimeters in front of the mirror. So just again with those signs, the object is positive when it's in front of the mirror, negative when behind the mirror. And so you got to be careful with that. Focal length, again, positive for a concave mirror, negative for convex. And then the image, positive if in front of the mirror, negative if behind the mirror. Generally, we call the object side of the mirror to be positive, and then all the other signs follow from that. So let's do another question here. The image produced by a concave mirror of a real object is what? Is it always real, always virtual, sometimes real, sometimes virtual? So think about this and we'll talk about it. All right, so I got that it's sometimes real, sometimes virtual. So the concave mirror, the focal length is bigger than 0, and the real object means in front of the mirror, so d0 is going to be greater than 0. So both those things are positive number, greater than 0. So we take our mirror equation, and if I solve that, I get over here. So 1 over di equals 1 over f minus 1 over do. So depending on how f or do operate, the di can be negative or positive. And remember, with the image, real means the light rays really do meet there, and virtual means that they don't. And so real will mean it's in front of the mirror, which is a positive sign. Okay, so for di, we just talked about. So positive would mean that it's real, negative would mean that it's virtual. And so with our equation here, depending on how f and d0 relate, it could be real or virtual. So di can be negative or positive. So all these kind of questions you can get from the mirror equation if you just know the right things to look for. All right, so we talked about the rays to use to find your image for a concave mirror. Now we're going to do convex. And so they're very similar, but it's a little bit different. So parallel to the principal axis comes in. So again, we draw a ray parallel to the principal axis, and it goes through the tip of the object. And what it does is it reflects as if it's coming through the focal point. Okay, so that ray there that I drew, if I backtracked it, it'll go through the focal point. And then we draw one through the focal point, reflects parallel to the principal axis. Okay, so this ray here, I'm drawing it as if it was going to go through that focal point. So it goes through the tip, and then I line up my ruler so it goes through the focal point, and then it comes off straight parallel. And then finally, so these two things, like we said, so this one comes in and bounces off as if it was shot from the focal point, and this one I'm shooting it in as if it's going to hit the focal point, and it bounces off straight. And if we backtrack those two guys, the tip is pretty much right about in there. And then finally, the same idea, if we draw one that goes through the center, it should bounce straight back in the same direction it came in on. That's a general rule with these spherical mirrors. And if I backtrack that one, it goes through like that. So it's definitely a good idea to actually get out a piece of paper and kind of draw some of these pictures yourself to make sure that it all adds up for you. So this image is going to be virtual. The light rays don't really cross there. It's upright, so it's in the same direction as the object was, and it's diminished. It's smaller than the object. And we'll find that for a real object, for convex mirrors, the image is always virtual, upright, and diminished. And the same exact equation, the mirror equation, works for the convex situation. The one thing that's going to be different is that, as we mentioned, the focal length is going to be negative. And so that's the one thing to be real careful about. That can really mess up your math if you don't remember that, because the problem usually won't tell you. So this one here, it does, but in general it won't. So here we give the same arrow placed 6 centimeters in front of a convex mirror with focal length -3 centimeters. Determine the image location. So we plug in this equation. Now it looks very similar to the last equation that we did. The numbers are the same. The one difference is is that this is a negative number, so this one's still positive. And of course, with a negative number, it makes a whole different answer. And you get DI equals -2 centimeters, which means the image is behind the mirror. Again, that agrees with what we got by doing our tracing, our ray tracing. Okay, so we'll talk more about this in lecture.